Imagine standing just meters from a collapsing skyscraper, yet the operator controlling its destruction sits safely hundreds of kilometers away. You never hear the operator shouting above roaring engines, because every movement happens quietly through wireless commands and live video feeds. That tiny machine survives falling concrete, flying steel, choking dust, and crushing vibrations that would threaten even experienced demolition crews. But here's what nobody tells you. Building one of these incredible machines begins thousands of kilometers away beneath the Earth's surface. Every hydraulic arm, steel track, and electronic circuit starts as raw minerals hidden inside mountains, deserts, forests, and deep underground mines. Most people see broken buildings, yet engineers see carefully controlled forces calculated down to astonishing levels of precision and timing. Each joystick movement controls hydraulic muscles powerful enough to shatter reinforced concrete weighing several tons within only a few seconds. Think about this. The operator feels almost no vibration, while the machine absorbs relentless punishment every single working day. Behind that incredible durability hides years of engineering, thousands of precision components, and manufacturing secrets few people ever witness firsthand. What happens next surprised even experienced engineers, because the journey becomes far more complex than simply building a powerful machine. Our journey begins in Western Australia, where iron ore rich in hematite forms the backbone of every remote demolition machine. Our journey begins in Western Australia, where iron ore rich in hematite forms the backbone of every remote demolition machine. Meanwhile, northern Chile supplies valuable copper, carrying electrical power through motors, sensors, cameras, and precision control systems. Without copper wiring, every wireless signal, hydraulic valve, and onboard computer would simply fall silent during operation. Think about this. One compact demolition robot may contain hundreds of kilograms of carefully engineered high-strength steel and specialty alloys. Rubber tracks begin as natural latex harvested across Southeast Asia, then transform into reinforced industrial compounds built for brutal conditions. Layers of steel cords reinforce each track, allowing astonishing grip while carrying crushing loads across unstable concrete debris. Rare earth elements from carefully processed ores strengthen electric motors that deliver smooth, reliable, and remarkably efficient machine control. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style. Crystal clear hydraulic oil flowing through polished valves, pumps, hoses, and cylinders inside. Photorealistic, cinematic, ultra-detailed, 8K, industrial documentary style, global logistics montage featuring cargo ships, freight trains, container terminals, and heavy trucks transporting industrial raw materials, dramatic sunset lighting, orange and blue industrial color grading, wide-angle lens, cinematic scale. Imagine one shipment traveling over 15,000 kilometers before a single steel plate even reaches the assembly factory. Heavy steel coils transfer from ports onto freight trains stretching nearly 2 kilometers, crossing mountains, deserts, and busy industrial cities. Powerful overhead cranes unload every component with astonishing precision, because even tiny impacts can damage expensive engineered materials. Every delivery undergoes chemical analysis, confirming alloy composition before manufacturing begins, protecting strength, safety, and long-term machine reliability. What happens next surprised even experienced engineers, because some imperfect steel never reaches production despite enormous transportation costs already invested. Rejected metal returns for recycling, where giant electric furnaces melt it into valuable raw material instead of letting waste accumulate. Recycling dramatically reduces mining demand while saving significant energy, making each new demolition machine more environmentally responsible than before. Yet raw materials alone cannot survive collapsing buildings until skilled manufacturers transform them into precision-engineered components. Behind those enormous factory walls, thousands of carefully planned manufacturing steps wait to shape every single powerful machine. And this is where it gets truly extraordinary, because next you'll witness steel transformed into unstoppable demolition power. The first sparks fly as thick steel plates enter CNC laser cutters, slicing with astonishing precision at temperatures exceeding 20,000 degrees Celsius. Computer-controlled lasers hold tolerances within 0.1 millimeters, ensuring every chassis component fits perfectly during final machine assembly. Next, robotic machining centers spin carbide tools at nearly 8,000 revolutions per minute, carving mounting surfaces with mirror-like accuracy. Coolant instantly removes intense heat, preventing microscopic cracks that could shorten the machine's working life under extreme demolition loads. Massive hydraulic presses then shape structural parts using forces exceeding 2,000 tons in only a few controlled seconds. You can almost hear the deep thunder as every press stroke reshapes steel into incredibly strong machine skeletons. Freshly formed components move into robotic welding cells, where blazing electric arcs reach temperatures above 6,000 degrees Celsius almost instantly. Shielding gas surrounds every weld, protecting molten metal from oxygen before it solidifies into remarkably strong structural joints. Experienced welders inspect difficult corners where human eyes still outperform automation in detecting subtle imperfections before assembly continues. But the chassis still lacks its incredible strength until the next fiery process permanently changes the steel from within. Inside the furnace, steel heats to approximately 900 degrees Celsius, or 1,652 degrees Fahrenheit, allowing its internal crystal structure to transform completely. The red-hot frame cools under carefully controlled conditions for nearly 4 hours, relieving stress before precision assembly begins. Next comes precision drilling, where computer-guided machines create perfectly aligned mounting holes within 0.05 millimeters of their design positions. Every hydraulic cylinder receives polished seals before technicians pressure test each unit beyond 350 bar, searching carefully for microscopic leaks. Hydraulic pumps deliver smooth power through reinforced hoses, sending pressurized oil racing faster than most people could ever imagine. Electric motors, cameras, antennas, and onboard computers connect through carefully routed wiring harnesses assembled entirely by skilled technicians. One misplaced connector could disable the entire machine, so every electrical circuit undergoes automated continuity testing before approval. Powerful rubber tracks slide beneath the finished chassis, transforming heavy steel into a machine ready to climb shattered concrete safely. Finally, the hydraulic breaker mounts onto the robotic arm, giving the machine enough force to pulverize reinforced concrete with ease. The machine finally stands complete, but proving its strength under brutal testing will reveal whether every manufacturing step truly succeeded.